Okay, so remember I said the amount of aerodynamic moment or hinge moment that you have to overcome, will also decide the stick force that the pilot has to apply, right, and it will also depend upon the lever arm that he has, but that cannot be too long or too short. It has to be at a comfortable level, so that every pilot can operate it in a comfortable fashion. Okay. So, and we said that there is one situation where elevator is free to rotate, right, that means the stick force is not required to change the elevator deflection, and that free deflection of elevator can be found out by setting the hinge moment to 0, isn't it? Right. So, we are talking about the hinge moment, and that hinge is here, isn't it? So, you have and this is your elevator, right. So, we said that we are going to set this CH to 0 and CH naught is actually 0 for symmetric airfoil. So, for this tail which is symmetric airfoil all the time, but canard is not a symmetric airfoil. Okay. There is the aft tail. Aft tail is usually symmetric, but canard may not be symmetric. So, there this CH naught term may not be 0. Right. So, when I set this hinge moment to 0 and assume that the aft tail is symmetric made of symmetric airfoil sections, then this goes to 0, and we found an expression for delta E free So, for every angle of attack at the tail, you can find a delta E free, right, and if I want to now start using the elevator, applying the stick force, what it means is you are not applying any stick force here, right, elevator has automatically assumed that position, isn't it. So, for alpha t which is positive, this delta E free is negative, which is upward, right. Now, starting from, so this is where stick force is 0, right. Now, if I want to deflect the elevator, I will deflect the elevator only from this point, right. Yeah, I have to deflect the elevator negative or positive, I have to overcome the aerodynamic moment starting from with this as the reference, right. So, where is this aerodynamic moment coming from, or the hinge moment is coming from the pressure distribution, right. So, if I call this only on this part, only on the elevator, this as Pu and this as Pl, right. So, delta E up, okay, from the neutral point will be decided by this, neutral position of the elevator will be decided by this, and beyond that, if delta E is up negative, right, what is happening? What is PL? PL and PU, which one will be larger? PU will be larger, right, because the camber is negative. Okay, so PU is larger in this case. Okay, so you are getting a lift downward, isn't it? So if PU is greater than PL, then which way the aerodynamic moment is acting on the hinge point? It's positive. You said it right, okay. So it's, isn't it? Now, so I have to overcome this moment, right. So what should be the stick force? I am deflecting the elevator up, right. So yesterday you saw that the mechanical arrangement was such that I have to pull Fs or the stick towards myself, okay, to deflect the elevator up, and that is Fs right. And the convention is that this pull they use as a negative stick force. Okay, I am not sure if I said something different yesterday. Okay, so let us use this convention. So this He, the hinge moment is positive. Okay. Required to deflect the elevator down, right. All right. Okay, but if you remember, we have been talking about the hinge moment considering this as the reference chord, right. This is where this whole action is taking place, right, pressure. Now I can only talk about the force distribution behind this hinge line, isn't it, and that moment only I am using to define the hinge moment. All right, what happens to this part? So let us draw a picture and a big picture here. Right, let us say this is the tail on which I have to locate my elevator. this is your hinge line. Okay. This part is elevator. What I have done here, I have extended this portion, right, so that it joins nicely with this part, isn't it? Why I have done that? So look at the aerodynamic moment that is being created is only because of the forces on this part, okay, no, the part behind the hinge line. What happens to this part? Now this is having a negative effect on the hinge moment, okay. So if you extend this part, no, in front of this hinge line, no, forward of the hinge line, that part is going to give you a negative moment, no. So when HE is being created because of this part, this other part of the flap or the elevator which is ahead of the hinge line is going to create a moment in the opposite direction. So it is negating that effect, right. So this is very important when you are sizing your elevator or designing your elevator. This is very important. The portion of
For delta E done, is it with respect to the delta E free or
delta E free, yes. Okay. So this part which is forward of the hinge line is also going to play an important role, right. Is going to have a contribution to the hinge moment. Is
always generally delta E measured as in with respect to the delta E free or with respect to the central?
actually this delta all I am talking about right now, you can measure the delta E with respect to this 0 line, okay, but what we are talking about is the amount of aerodynamic moment that you have to overcome by applying the stick force, okay. Then it has to be with respect to this delta E free.
But even when the elevator delta E is above that, even when the elevator is above that free point, it can still have a positive.
Actually you can adjust that. That adjustment is made by using the setting the tail incidence angle. So you can have, but that may not be changing at every alpha t, right. So this is only if, can be used as a reference for calculating the aerodynamic moment. Accordingly you have to find how much stick force you have to apply, right. Portion of the elevator forward of the hinge line is having a negating effect, okay. Right. So I have to actually decide how much forward, how much surface I want forward of this hinge line on the elevator, because I want to reduce the hinge moment, because that will reduce the work load on the pilot, isn't it. So this sizing is called aerodynamic balancing. Okay, you can read this. So our effort is actually to reduce the pilot workload. Usually in a transport aircraft which is designed for long flight, there you don't want to burden the pilot. So there what they will use is the surface for setting the trim. That surface is called trim tab. Okay. So trim tab is a small surface located at the trailing edge of the elevator. So if you want to look at this section, what you see is this. What do you do? What is our idea? We want to cancel this hinge moment, isn't it? So now if I want to include this trim tab to make this hinge moment 0, which is about this hinge line, okay, and is free to rotate. So moment about this point is already 0, right. Look at what is happening. It's not going to change the lift on the tail much with such a small surface, right, but the length, arm length that it has is quite large, isn't it? So it's actually going to give a significant moment, but very small lift, negligible lift. Now let's look at this expression again for the hinge moment coefficient, that is so I want to trim the aircraft at a particular elevator setting, right, and I want to find out the trim tab deflection, free deflection, so that the moment at the hinge point is 0, right. So what will the pilot do actually here? Now he only has to play with this tab and not with this whole elevator, right. So once he sets the trim tab, he is actually setting the elevator angle. For any free trim tab deflection, elevator angle will be automatically set, right, and you can achieve different elevator trim. Okay. So he has to only play with the small surface, so he has to probably not even actually have to apply any force, he can do it through some gear arrangement. Okay. Right. So if the elevator is downward, which way the trim tab should be? Upward, right, is understood. Okay. Why we are changing the elevator deflection? Because we want to change the trim speed. We want to fly different speeds, right? So actually delta E over delta CL should also be somehow related to this, right, this gradient, isn't it? Because when you talk about a level flight condition, when you are changing, let's say you want to fly at different speed, what you have to change? You have to change the CL trim, and CL trim you change by deflecting the elevator, right? An elevator is being controlled by the stick force, isn't it? And that is so somehow these two must be related, right? And if you remember, we said that this is related to the static margin, or probably this is dCm over dCl, right? Okay. So this is related to the static margin, right? And static margin is giving you the stability, isn't it? So stability, more stability we have, the more control that we need to change the trim, right? This we have discussed. So what it automatically means is that this gradient of the force with respect to the trim speed is also dependent upon the stability margin, stability of the aircraft, right? Is this clear? So this quantity is actually depending upon the stability of the aircraft. So where do you think that stability of the aircraft will change? We have talked about a free flying condition, right? We are flying at some altitude, isn't it? Let's say we are coming down and approaching the runway, right, about this landing situation. Do you think this is going to change? Or any other flight also where you have this thing changing, is automatically going to affect this elevator requirement, and it's going to affect this, right? All of them are connected. Is this clear? So let's try to tell you where the workload on the pilot may increase, even if it is not there in, let's say, cruising condition. This minus, I think is there, you can check back in your notes. Okay, let's try to find out what this derivative is. Okay. This is called control force gradient or stick force and it is related to aircraft speed stability. So let us first try to find out an expression for this force in terms of the hinge moment. So Fs is He over Ls. Ls is the, remember I drew this picture. So Fs is actually He over Ls. Okay. Now again the expression that I gave you yesterday was based on the work balance, right. Here is the moment balance, right. So let us look at this. C is this length into CH. So this CH is now sum of all the terms. Okay. There is an expression which has been worked out in the book that just now I referred to, okay, Mechanics of Flight by Phillips, and this expression for the stick force is this. This includes the maneuver effect, okay, maneuvering. So N is the load factor here, L over W. Actually there is a nice derivation which gives you this, okay. So this expression has been derived, this is not an empirical relation, okay. So what we have to do, we have to find out what this derivative is, okay. So what we are trying to do is, we are trying to look at this force through which pilot is going to get a feel for the stability, right, or this gradient which the aircraft should possess in some fashion, okay. So to counter the effect of change in stability from the trim speed, okay. For subsonic flights, actually we can find an expression for this control force gradient at constant load factor and a trim speed which is and if you want to find out the longitudinal force per g, that is given by this of course, you do not see any anything defining the stability here, right. So, you would wonder why this would be related to stability, but I have not given you the expression for C1 so far, and this is so clearly Cm alpha is appearing here, right. So, this force gradient is depending upon the stability. The longitudinal force per g is also going to depend upon the stability, right, because C1 is a function of Cm alpha and C2 is C2 is 2 into LT tail arm length CH alpha t over C bar mean aerodynamic chord of the wing CL delta E CMQ minus CLQ CM delta E CH alpha tail into 1 minus epsilon, epsilon is the downwash minus CL alpha CMQ minus CLQ CM alpha CH delta E over CL alpha Cm delta E minus CL delta E Cm alpha. Okay, there is a big expression. Okay, but all it's indicating is longitudinal force per g, which is this. is going to depend upon these factors, right. You would notice this Q appearing here, right. Q is the pitch rate, okay. When you are trying to do a pull up maneuver, right, there a rate is involved. You want to pitch up the aircraft, right, when you want to do a pull maneuver. So that is where this these derivatives are coming into picture. Okay, let's try to quickly see what actually this means. Okay, so I am plotting here the stick force against speed, and this curve is somewhat like this. Okay. So let us try to find out the slope of this curve at Fs, which is 0. Okay, that is the trim speed. What should be this force for stability? What should be the sign of this gradient? When you change, but right now this slope is what, positive or negative? It is negative, right, and this indicates speed your airplane should have this property if you want it to be stable with change in speed. Okay, and let us see what is happening. If you are changing this, let us say there is some disturbance and the trim speed is changed, it is reduced. So what is the stick force? Stick force is should be positive, right, and for that the elevator deflection should be downward, and downward elevator deflection means a downward pitching moment, isn't it? So this is also related to the pitch stability in some ways. So if your aircraft is having this pitch stability and you are keeping your hand on the stick, then you will automatically feel it. Okay, so you are flying at trim speed, and let us say the speed changed in flight, disturbed change. Okay, it is not a big change, but a small change, and immediately you will feel a force on the stick, right. So that is what it means, right. So now let us try to, so clearly the flight in free air is going to be different from the flight very close to the ground, right, and all those effects, so all those parameters that you see there are going to be changed, modified when you are close to the ground. Okay. So one of the main effects, okay, is that downwash angle at the tail is going to change, and that is going to change which way? It is going to increase or it is going to decrease? It is going to decrease. Downwards effect is going to decrease when you are close to ground. So, this is one of the major effect. Okay. Landing is a critical maneuver, it is not a many accidents will occur while landing. So, landing is actually a critical maneuver, and you have to actually take into account of effects that are taking place close to ground, right. So, you have to change those derivatives. Downwash is going to decrease, right. What is it going to do if the downwash is going to decrease? Is going to change the trim and stability characteristics both, right. So, pilot should know that when you are trying to come down, you are going to actually from the cruise condition, you will initiate one the approach maneuver, there is approach, and finally landing, right. At landing, what do you expect? I mean, it should be landing at what CL? CL max actually, right. I think I will continue from here in the next class. Any question?